Yes. Good afternoon. My name is Jaesub Hong from Harvard. Let me tell you a little bit about our mission concept, CubeSAT X-ray Telescope, CubeX. CubeX is a joint program between many institutions, including Smithsonian Astrophysical Observatory, where PI is Suzanne Romaine in the audience. And we are collaborating with Harvard and MIT and many other institutions. And locally, here in the UK, we are consulting with Professor Ian Clark at the University of London to get learn more about the moon science. And the spacecraft and mission operation is worked out by NASA Ames Mission Design Center. So this is outline of the CubeX, which is basically 12 CubeSAT instruments. So it is a somewhat unusual form factor, as you can see. The instrument is about half of the spacecraft. Along this direction, we have one new unit in order to get the 50 centimeter focal length, and the other half is devoted to the spacecraft. Basically, it will be it'll take a rideshare to a moon as a secondary spacecraft on a primary mission, and it is selected as one of the 10 mission concepts for NASA's planetary science deep space small set studies for the next 6 months. So we have two science goals for CubeX, which is somewhat generic actually, not limited to moon. Basically, the first one is the map surface elemental composition of diverse Airless bodies using the X-ray fluorescence spectroscopic measurement, which allows us to understand formation and evolutionary history of these target bodies. And then the second goal is actually conduct the feasibility and performance test of the X-ray pulsar timing-based deep space navigation, which is called XNAV, which allows to, if it is successful, which allows to lower the operation cost for deep space navigation in the future. So the current mission concept for CubeX is designed for Moon, because the Moon has also a lot of interesting science to do once you learn about the elemental composition in detail. And also, as for the XNAV, since the proximity to the Moon allows to test this feasibility of XNAV very easily, so that is a somewhat obvious choice going forward. So to give you a little bit of the reminder for X-ray fluorescence, so as you may remember, the X-ray fluorescence coming from either interaction from the incoming X-ray, in this case the solar X-ray, depending on the surface of the moon. The interesting thing about X-ray fluorescence is the energy of the fluorescent X-ray is unique to the atomic level. So it is a kind of decisive probe to the elemental composition. And in the soft X-ray band, somewhere from 0.2 to 15 keV, you can cover most of the key elements. And especially what is interesting about the X-ray spectroscopic measurement relative to optical or infrared is it can probe about 20 micron or more below the surface. So regardless of the space weathering, which can alter about a couple of micron down the surface. So sometimes those space weathering can fool the optical or infrared spectrum results. However, X-ray fluorescence spectroscopy can give you a truthful elemental composition. So here I'm showing an example of simulated X-ray fluorescence spectrum from actually an asteroid of CI chondrite composition. As you can see, there's lots of lines. And what you can do about measuring these lines in the case of asteroid, you take the ratio of them, then you compare with the known meteorite specimen, then you can classify those asteroids. And in the case of X-ray fluorescence measurement in planetary science, there's a number of experiments. In the case of the moon, starting with Apollo, it didn't quite measure the whole surface of the moon. And then lately, there's a successful conclusion of the messenger mapping out the full surface of the Mercury. So what we are trying to bring in terms of the instrument technology into the planetary science is bring the focusing X-ray telescope, focusing instrument. So in the case of a big target like the moon, you can imagine you have just a small collimator instrument with a footprint of about 10 to 20 degree field of view. Then you'll have a surface footprint of about 20 to 40 kilometers. Then you just circle around in a lower lunar orbit, then you can map it out. However, the problem with that is the orbit period is relatively short, and sometimes we have to rely on the strong solar flares to get the signal. And you only stay about 10 or 20 seconds for a footprint. So even though you get a big flare lasting a few minutes to hours, you're not getting signal from the one spot, so you're just diluting the signal. So the idea we are bringing is if we have a focusing optics, instead of staying in a lower lunar orbit, you can start with a high altitude orbit. In this case, elliptical lunar orbit. And then you can, let's say you have about an approximate angular resolution with about degree square field of view. And what you can do is you choose a few regions of interest targets where you can have about footprint of 50 to 150 kilometers with about 1 to 2 kilometer resolution. And then you can stare at them for a few hours. Since your orbital period will be long, you can stare at each spot for a couple hours. So when flare happens, you can collect all the signal from those flares. And then another thing nice about this kind of orbit is related to our secondary objective doing the pulsar observation to prove the XNAV technology is that it also requires a couple hours of long integration. So when you go to the night side of the orbit, you can look at the pulsar continuously. So that's our approach. On this slide, I'm listing some of the moon science we are particularly interested in. Mainly, we are trying to understand the composition of the moon, especially identifying the regions of the surface, regions of the moon where maybe rudimental material being excavated due to the big impact. And the moon scientist tells us identify this monumental can help us to get an insight on how moon's formation occurred. And also, even if we don't identify even metal material, by looking at the different size of crater, you can actually explore different depths of the composition. And then also, you can also explore some of the young lava floors. And then, of course, the objective is somewhat questionable at the moment, whether it can be doable or not. But if it's possible, it will be very interesting because using charge interaction, charge exchange interaction between solar wind and then neutral hydrogen on the surface, there is a way to generate the fluorescent light. So you can see the composition of the permanent dark side of the moon. However, this is somewhat controversial at the moment. The reason is the signal seen from the dark side of the moon by Rosette and Chandra satellite, which we are basing on this goal. However, latest Chandra observation tells us they may not be coming from the moon's surface. It's coming from the Earth's geocoronal volume. Nonetheless, looking at the dark side, we can actually, if we don't see anything, we can use that as a setting our baseline for the instrumental background, so it will be still useful. So these are the sort of moon science we are thinking about, but any of you has a better target for it, then please talk to us. And this will be the sort of current version of target regions we selected. And we are going to revise them. The idea is we choose about 20 target regions, and then we prioritize them. And then we try to get about a millisecond exposure among at least the first 10 targets over 1 year mission lifetime. And then going to second objective, which is the observing the X-ray pulsars to get the navigation information. So the idea is using millisecond X-ray pulsars and then measure its pulsar profile. Then given the precision of the pulsars, we can use it as a sort of GPS signal in unit. And then if you observe one pulsar and then identify this the peak position of the pulsation profile, then you can identify your spacecraft location along the direction of the pulsar. And then if you make a similar measurement successively for multiple pulsars, then you can identify your spacecraft location in 3D without need for contacting ground or space communication. So those are the two main objectives. Here I have the example observing sequence in an orbit. So here's the sun. So when you are at the base side of the orbit, you look at these target regions depending on the viewing condition, how favorable they are, and you stare at a couple hours each. And then once you go to the night side, you will observe the pulsar. In the case of the target on the moon, we really need to collect enough exposure to get enough signal. The idea is we get about million photons or more from each target, and then we have about 1,000 elements or pixel elements. Then each pixel element will have about 1,000 counts. In the case of pulsar, we don't have to observe every single orbit, so we have some room. If we need to use that as a communication, then we can plan that. So next two slides, let me tell you a little bit about the technology which enables this kind of measurement. So first thing is the optics, X-ray optics. I don't know how much you guys are familiar with. This slide sort of summarizes the advances happening in X-ray optics, starting with the Chandra using the zero-look glass, which is the best X-ray telescope in terms of angular resolution at the moment. However, it's very heavy. So what people have been pushing is replacing this heavy material with a lighter element. In this case, actually, it's a metal, the nickel or nickel cobalt, but you can make it very thin. So effectively, you can make it light, and also you can stack them in large numbers. What we are trying to do, we have actually Picasso program. The NASA's Picasso program developed new types of the X-ray meter, which is basically metal ceramic hybrid shell. What you're trying to do is you replace majority of the heavy metal material with the ceramic, which is light, but it provides stiffness to hold the figure, and then remaining metal gives the micro roughness to reflect the X-ray. So we are developing this new types of meter. However, for CubeX itself, the meter we are trying to develop fits in the 1 cube unit, which is very small. So I think we can get away with the current leading edge technology, which is just simply using thin nickel cobalt. What we are trying to do is make it even thinner, less than 200 micron, based on some of the models we already built. And then we have a very interesting focal plane technology, since we have two major different objectives. So here we employ two monolithic CMOS X-ray sensors in side by side, and this red thing coming down is actually field of view covered by our optics. And as you can see, field of view itself is completely covered by the CMOS detector, but we employ two in order to have a silicon drift detector behind it. But the idea is the CMOS detector is pixelated. It's about 1,000 by 1,000 pixels in 1.6 centimeter by 1.6 centimeter. So it will be used for doing the XRF imaging on the moon surface. However, it doesn't have a timing resolution. You need to do XNAV. So what we try to do is that when we observe pulsars, we have a small gap between these two CMOS detectors. This blue circle is the field of view. And when we observe the pulsars, we orient the telescope so that the pulsar falls in between the gap of the CMOS, and then let the X-rays from the pulsars go through and then detected by the silicon drift detector, which has some microsecond timing resolution. So that's our idea about focal plane. This allows us to do these two somewhat different target observation without any moving parts. Okay, so this is my final slide. which is just summarize the mission overview. So we are designing this mission concept as a secondary mission going to the moon, and we are assuming we'll be inserted as a high altitude orbit. Right now, actually, we are exploring the high altitude frozen orbit, which also give us very favorable condition in terms of maintaining the orbit. Since it's frozen, we don't have to do much, stay in that orbit. And we have two new kind of technology, both in optics and focal plane, in order to make this possible. And main scientists, they're looking at the 8 or 10 interesting regions on the moon to understand the analytical condition and also perform the pulsar navigation measurement in order to see how feasible this technology is for the future. Thank you.
Any questions? Thank you for the talk, it was really interesting. I was just curious, because the size of your CubeSat is quite long. Is that a challenge for you don't really have a standard deployer for that, I take it?
Yes, we consider it as one of the risk items, whether there will be additional substantial work required for making this happen, or maybe small modification will be enough. So that's something we are looking into. So I don't have an answer for you yet, but we are identifying that as a risk item.
Okay.
Can you comment a bit on the pulsar-based navigation? How many sources you need to have? How much is the accuracy that you have on the position and so on?
So there were quite a few papers actually in the literature, and we are basing on a couple of papers actually from European studies, and also, as you probably know, this weekend or next week, the NICE mission, Nuclear Interior Collision Explorer, will be launched. And NICE mission is actually will demonstrate this XNAV capability in the International Space Station. And they listed about in their paper, they listed about 60 pulsars which can be used this kind of studies. And then the paper, Shimar 2016, listed about 80 pulsars. And for us, our telescope is a little bit smaller end of it in terms of the effective area. So in the first order study, we think that there are 5 or 6 pulsars who can do these studies, like observing about a couple of hours, which can give us about 5 to 10 kilometer precision in the spacecraft. So that's the order of the number of pulsars we think we can do.
So I hope I'm not at all. So I saw in one of your diagrams you've taken your measurements on the day side and then plunging towards the pulsars afterwards. Given the size of your satellite, how many times are you going to be able to do this slewing to and from the pulsars into the
we haven't worked out completely, but like I mentioned earlier, pulsar observation we don't need to do every single orbit. We only need to do once in a few weeks. Because we just need to demonstrate this is possible and how much accuracy we can get. And we'll get some bright pulsar and marching down. So probably observe maybe 5 pulsars or 10 times, so maybe 10 orbits will be spitting out.
Okay.
So it doesn't have to be that often. So we try to see if that is feasible. That is also our one of the concerns.
Okay, thank you very much. Oh, sorry, there was one more question.
Are you able to perform fine pointing for the telescope, and if yes, how do you do that?
Well, that's something we are getting advice from the NASA Ames Mission Design Center. In the initial their assessment, they said there's no big showstoppers at the moment. But to give you some idea, when we look at the moon surface, we need about 2 arc minute pointing capability. For the pulsar, since our gap is 2 arc minute in our detector, we need to have a 1 arc minute pointing, which is some of the challenges we need to overcome. And then we have to employ multiple star cameras or terrain trackers in order to accomplish both science at the same one package. So we are looking into that, but at least they are telling me it's not a red sign yet. So.
Okay, thank you very much. Thank you.